Okay, should be recording now. All right. I mentioned this problem yesterday, and this is kind of a fun one. This is the OMG particle, this crazy high energy cosmic ray proton. And backtracking, they determined that its kinetic energy was about equal to a 50-mile-an-hour baseball. Now, something I'm going to do is just assume that we have two sig figs on that. So we get a little bit more in the number range. It's kind of a drag when you have to round everything off to just one significant figure all the time. So, but the first thing we'll do is calculate gamma for one of these protons. Well, things that we're going to need to know to do this is, first of all, for something that's got a very high energy, or in general, actually, the kinetic energy is equal to gamma minus 1 times mc squared. And I don't remember if I'm the one who wrote this problem or not, or if I ran across it somewhere, but it says if they have kinetic energy. So that's the kinetic energy, except in this case, the total energy just doesn't have the minus 1 in there. It's got gamma mc squared. And if gamma is a pretty large value, there isn't much difference between gamma and gamma minus 1. And I think we did an example last night where we saw that that was the case. So it might be one of those two things. Now, the baseball, 50 miles an hour, is not a relativistic particle. So for it, we'll just use the kinetic energy is just going to equal 1/2 mv squared. 50 miles an hour, I calculated it this morning. If it's two significant figures anyway, it's about, well, if you just do this, miles per hour times 1,609 meters per mile times 1 hour over 3,600 seconds. The velocity, I'll call this v sub bb. It's about 22 meters per second. So good enough. And then the mass of a baseball, m sub bb, is about 0.14 kilograms to two significant figures. So not a whole bunch. So the kinetic energy of the baseball, which I could label as K sub E BB as well, is just 1/2 times 0.14 kilograms times 22 meters per second squared. And turns out it's about 36 joules, but I may check that just to make sure. Times 4 times 2. Okay, actually it's about 34 joules, so a huge amount. Okay, actually not that much. But that's going to be also the energy of this high energy proton. Now we can figure out mc squared for a proton, and then we'll be able to set this thing equal to this thing and figure out what gamma happens to be. So m sub p c squared is going to be 1.67 times 10 to the minus 27th kilograms times 3.00 times 10 to the 8th meters per second. That's messy, squared. The mass of the proton times c squared. I did it before, but I got about 1.5 times 10 to the minus 10th joules, but I'll check that just to be sure. Yeah. Um, okay. So for that proton, if we use either gamma minus one or gamma, it turns out it's not going to matter, but we'll have that gamma mass of the proton times c squared is going to equal 34 joules. And so gamma will equal 34 joules divided by 1.5 times 10 to the minus 10th joules, which is gamma's dimensionless. I get about 2.3 times 10 to the 11th. Okay, with a number that big, there isn't any difference between gamma and gamma minus one, or not enough to matter. So we'll just figure that this is the total energy of the proton, because it's so much greater than the rest energy of it. So that's our gamma value. Now, what's the difference between the speed of these protons and the speed of light? Here's the thing, you could, knowing that gamma is that, somehow try to find out what the speed of the proton is just by itself. But I think you'll see pretty quickly that we're going to lose it in the the tail end of a whole bunch of digits. But let's go ahead and work as far as we can on that. Now remember, gamma is, I'm not going to use that number until I absolutely have to, but I'll just know that that's what gamma is. Gamma is 1 over the square root of 1 minus beta squared. And remember, in this context, beta is equal to V over C. And eventually we'll use this for it, but it's just shorter to write beta for a while. So if I square both sides of this, I would get that gamma squared is equal to 1 over 1 minus beta squared. If I think of this as gamma squared over 1, I can flip both sides, and I get that 1 over gamma squared is equal to 1 minus beta squared. I'm going to kind of work in columns here. Or beta squared is going to be 1 minus 1 over gamma squared. Or, coming up here, beta, which is V over C, is going to be the square root of 1 minus 1 over gamma squared. Now, gamma is a pretty big number. Gamma squared, this would be something like, I don't know, 5 times 10 to the 22nd. And 1 over gamma squared is going to be pretty darn small compared to this 1. So at some point, we're going to expand on this square root, but not just yet. Okay, now we're going to recognize that beta is V over C, and that V will equal C times the square root of this thing. And this thing is going to be so close to 1 that it'll be a 0.99999. I don't know how many nines it's going to have, but it'll be a whole bunch. And so that'll be problematic. However, the question says to find the difference between the speed of the protons and the speed of light. So let's look at this. C minus V will equal C minus C times that square root of 1 minus 1 over gamma squared, or C minus V will equal C times 1 minus the square root of 1 minus 1 over gamma squared. Okay. Now, we've done some tricks like this before, although it was always with things that were going slow, where we'd have 1 minus 1 V squared over C squared. This will work the same way. And so if we evaluate the stuff inside here, we'll get a number, and we can multiply that by the speed of light, and we can use the exact speed of light if you want to, although because we didn't have that many significant figures, we should probably limit ourselves to 2 significant figures. But if we just use 3.00 times 10 to the 8th and multiply it by the result of this, we'll find out the difference in the speeds between those two things. So now it's time to do a series expansion on this thing. And remember that 1 plus x to the n is equal to 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus other terms in the series. And we're going to end up throwing this term away anyway. But see, it'll be this 1 plus nx, and we've got 1 minus this series. And so the ones are going to vanish, and the first thing that's going to be left for these parentheses will just be the nx. Well, let's see how this is going to work out. For us, n, the thing that our square root is a power series of, is going to be 1/2. And x is going to equal minus 1 over gamma squared. Okay. All right. And so this square root of 1 minus 1 over gamma squared, I hope this is still, I've got too much stuff up here. Hope that's still legible for you, that you're not watching this on a phone. That will become, okay, we've got 1 to start with, plus n, which is 1/2. And x is minus 1 over gamma squared. And then the next term in the series, we can do it in our heads. It'd be 1/2 times minus 1/2 over 2 factorial. That actually ends up being minus 1/8. And then instead of minus 1 over gamma squared, that's what x is. I've got x squared, which will become positive. So it'll be 1 over gamma to the 4th. Let's see. And this one has a minus sign too. So this square root ends up equaling 1 minus 1 over 2 gamma squared minus 1 over 8 gamma to the 4th. Okay, well, when I do this parentheses, I'll get that c minus v is going to equal c times, it's 1 minus that series. So 1 minus 1 is 0. It'd actually be 1 over 2 gamma squared plus 1 over 8 gamma to the 4th plus you'd have other terms in the series, but they would actually end up being even smaller than this one. So let's go ahead and figure out what those are going to be. And I'd have, I guess I've got room. C minus V is going to equal C times, okay, 1 over 2 gamma squared. So 1 divided by, turn on calculator first, 2 times gamma here somewhere was, 2.3 times 10 to the 11th, and I have to square it. So 2.3 EE11 squared. So that first term in the series is 9.4, actually 9.5 times 10 to the minus 24th. The second term in the series is going to be 1 over 8 gamma to the fourth. So let's see if I need to keep it compared to that, and I won't. But anyway, 1 over 8 times 2.3 times 10 to the 11th. Raised to the fourth. Yeah, the next term in here is going to be 4.5 times 10 to the minus 47th. Let's see. So you start off with a decimal point, you'd have 46 zeros, and then you'd get that 4. This one's bad enough. You'd start off with a decimal point, you'd have 23 zeros, and then get to the 9. But this one's even worse. So we could ignore this thing. And we just take c minus v is equal to this thing times the speed of light, or c minus v equals 3.0, I'm only going to keep 2 sig figs, times 10 to the 8th meters per second times 9.5 times 10 to the minus 24th. And c minus v is not going to be much. Let's see. I'll go up and use that number so I don't have to punch it in again. Okay, and I get not much. Actually, I could round it to one significant figure, just call it 3, but it's 2.8 times 10 to the minus 15th meters per second, which is that's roughly the diameter of a nucleus, or maybe the radius of a nucleus, depending on which nucleus it happens to be. But that means it would take, I don't know, 1/3 times 10 to the 15th seconds before it even travels a meter, or before a photon would get a meter ahead of this particle, I guess I should say that. So for practical purposes, this cosmic ray proton is going at the speed of light, because that's the difference between its speed and the speed of light. So it's just crazy fast and very high energy. So yes.
What was the reason for using the series expansion? Because I'm curious, could you have
Oh,
just solved it without it?
no, because if you tried to just calculate this, you'd get 1 on your calculator. Your calculator doesn't have enough significant figures to do this.
Oh, okay.
Yeah, because you'd be subtracting an extremely small number. Actually, 1 over gamma squared is 1 divided by 2.3 times 10 to the 11th. Yeah, just this 1 over gamma squared is 1.9 times 10 to the minus 23rd. So you'd have on this, you'd be going 1 minus 0.000, 22 zeros before you got to a non-zero digit. And there just aren't calculators that bother to keep that many digits in their memory. So, and so this was the only way we could really do it.
Okay, thank you.
Mm-hmm. Yeah, but kind of a fun problem. Sort of crazy stuff. Let's see. Here's one that looks at vanishing mass. And in this case, it's looking at the nuclear reaction inside the sun, which it's actually a 3-step process. But if you look at what you start with in that process, which is 4 protons is all it is, and what you end up with, which is 1 helium nucleus, a bunch of leftover energy, and 2 positrons. somewhere here. Let's see. Yeah, it's got the mass energy of each of these things. And we're supposed to calculate the percentage of the initial mass that is released as energy, and that would be the delta E. So this energy, if you set this up as an energy equation, you'd have to have energy is conserved. And so what you'd have for the initial energy is 4 protons, and the mass energy of a proton is that much. Well, the energy of the proton, you just take away the c squared, and you'd have the energy of that proton. That'll be 938.272 MeV is the rest energy of a proton. So we've got that. And the final energy is going to be the rest energy of that helium nucleus, which is, or the mass energy, it's 3,727.379 MeV. This is proton. And so we'd have 3727.379 MeV. That's the helium nucleus. And we'll have some amount of excess energy or some more energy on this side, delta E. And then we've got the 2 positrons, so I have to take 2 times the mass energy of a positron, which is 0.511 MeV. So, and in this case, it's just easier using MeV for these things. So the delta E, if we solve for that, it'll end up being 4 times that 938.272 MeV minus 3727.379 MeV minus 2 times 0.511 MeV. So this is just a conservation of energy expression for what we start with and what we end up with. And we can figure out how much energy there is left over. And then we'll calculate the percentage of the initial mass that is released as energy. So we can think of this delta E as equal some missing mass times c squared. It's actually what we can think of it as. In fact, that's what all of these things are. So, time to plug this into a calculator. Yeah. Turn on calculator. Oh, I've got all these sig figs showing. I might need them on this problem, actually. What I get for this is 3753.0880 or 088 MeV minus this 3727 minus that stuff. I was just curious what that one would happen to be. And actually, it's good to know this. This is what we start with. So minus 37.379 minus 2 times 0.5. And I actually get, anyway, the delta E ends up being 2.4687 MeV. Wait a minute, that's 24. So the decimal point belongs here, 24.687 MeV, which is a fair amount, actually, even though it's out of roughly, what is it, 3,753, but 24 isn't insignificant compared to that. So it's a fair amount of energy, and that will equal some, we can think of it as a delta M times C squared, although, let's see. Actually, we could just take this and divide it by that initial mass energy. And that'll tell us what fraction of that initial energy is released as energy. And that's equal to the fraction of the initial mass that's released as energy. So, yeah, delta E over the missing E over 3753. Oh, if they want a percentage, times 100 will equal the percentage. So I got the 24.687. I'll divide that or multiply it by 100 and then divide it by 3753. And you get about 0.66%, which doesn't sound like much, but there are something like 10 to the 37th reactions per second that are producing those particles in the core of the sun. So that's a lot of energy, and it ends up being something like roughly 3.4 times 10 to the 26th watts is the power output of the sun. So it's a lot anyway. So, but it's almost a percent, and there aren't chemical reactions that approach that. Maybe they might be a millionth as efficient as that in a chemical reaction, in the best chemical reactions. So that's a reason that chemical reactions, the typical energy released in one is measured in electron volts, and for nuclear reactions, we're measuring them in mega electron volts. And so not very much, but that's just playing around a little bit with MC squared, and the fact that for things like protons, it's more practical to use this as a unit of its mass. This isn't actually the mass energy of the proton. This is mass, because if you take its rest energy and divide by c squared, you actually do get mass. So these are weird units, but they happen to be units of mass. Okay, I had just a couple other basic problems that we could do here, kind of final ones. And these are just time dilation problems, but they're kind of interesting. I cut and pasted these things from the OpenStax textbook, and this is supposed to be an exponent, minus 16, and so is this. And so the formatting I had to correct. I corrected it on this one. But suppose a particle called a kaon is created by cosmic radiation striking the atmosphere. It moves by you, the kaon does, at 0.980 C, then it lives 1.24 times 10 to the minus 8 seconds when at rest relative to an observer. How long does it live as you observe it? Okay, this is one of those moving clocks run slow thing. And the time that you are going to have to observe it is going to equal, you take its internal clock and do what you say this is going to run slow. This time is going to get stretched. It's a time interval in the thing of the kaon, and you're going to say, hey, your clock is running slow. Your time interval is taking too long. So we multiply this by gamma. And so the t that you observe is going to equal gamma times the t that the kaon observe. And I guess may as well just use a k for the kaon. I don't know if that's a real particle, if this is just made up, because there is a particle that's got a half-life that's down around that. Or what they call it a lifetime, but it's actually the half-life of a whole bunch of these particles. But let's figure out gamma in any way. It's 1 over the square root of 1 minus v squared over c squared, but this is v, and so if we divide that by c, we get 0.980, so it's 1 minus 0.980 squared. When I took, I guess it was a junior level course in special relativity at Eastern, and I ended up calculating gamma so many times that I had a program built into my calculator for doing it, but it's easy enough to stick in there. So it's just 1 divided by square root of 1 minus 0.980 squared. And I get 5 point, how many, we have 3 sig figs, so 5.03 is what I get for gamma. And so the time that's observed by you is going to be 5.03 times that 1.24 times 10 to the minus 8 seconds. Okay, which isn't a whole lot longer, 6.23 times 10 to the minus 8 seconds, but it'd make it last 5.03 times as long before it decays. Now, if you multiply that by the speed of light, which it's nearly traveling at, it's still not going to go very far. Yeah, it's only going to go about 18.7 meters before half of them decay. So if there is such a particle as this with that short of a lifetime, you're going to have to somehow have things up there in the upper atmosphere to detect them, because they're going to decay, a lot of them, before they reach, nearly all of them before they reach the surface of the Earth. But in the early days of cosmic ray studies, they would float the cosmic ray detectors on balloons and keep them a lot of times shielded in a lead box or a lead lined box, and only expose it to the cosmic rays when they got to whatever altitude they were interested in. Like they float them up to 120,000 feet or something like that. And up there, you're above about 99% of the atmosphere. The Earth's atmosphere acts like, well, it absorbs cosmic rays in about the same proportion that a meter thick wall of lead would do. And so it essentially stops most of them, but some of them do get through, like those crazy muons do. So there's that. Okay, and then there's one more time dilation problem. The neutral pi meson is a particle also called a pion. Particle, it can be created by accelerator beams. one such particle lives 1.40 times 10 to the minus 16th seconds as measured in the laboratory, and 0.840 times 10 to the minus 16th seconds when at rest relative to an observer. So in the laboratory, this thing is flying past you at a high speed. What is its velocity? So here we've got a t prime, which is I'm getting the rest time is longer than the laboratory time. I wonder if there was a mistake when I copied this thing. Okay. Yeah, I'm not crazy about the way this problem is worded, because usually, as measured in a laboratory, what you would be getting is a particle at rest, but this one says 0.840 at times 10 to the minus 16 seconds when at rest relative to an observer. This would be like its proper time, which in this case is longer than the thing that you'd see in the laboratory, which is usually the at rest time. So that doesn't make sense to me, that you don't have a moving clock that runs fast. So let's toss that out. I'm going to have to make sure I didn't miscopy that problem. That could be. Okay, or maybe that's just a weird problem. Well, we did get through 3 small problems today anyway, and the one that I get kind of a kick out of is being able to use that infinite series on this problem to you can't figure out the speed of the particle because it's the absolute speed of the particle. So it's because it's so close to the speed of light that to all the digits in the exact speed of light, it's exactly the same. But we were able to, wherever I put the solution to that. Oh, I probably tossed it. Anyway, we were able to figure out the difference between the speed of this thing and the speed of light, and it ends up being really small. 10 to the minus 15th meters per second, which is let's see, something like 10 to the 23rd times smaller than the actual speed of light. And that's kind of remarkable. And they just discovered another one. And now they've observed a few of these things, they've got an estimate for about how often such particles strike the Earth, which I don't remember what the number was, but I did read an article about that thing, the most recent discovery of one, and it seemed like it was just this past winter. So at any rate, there we are. And what day is today? Tomorrow we've got a regular class day, but we could actually start reviewing for the final if you want to look at the review materials, or if you want to look at the homework assignments and see if you might have questions on them. But we could kind of have tomorrow as a review day for the final. So please come equipped with questions, and we'll see what we can do tomorrow. Okay, I will stop recording here and see you tomorrow. I think, yeah, today's Wednesday, tomorrow's Thursday.